Hello, my name is Frits de Mul and I would like to introduce you to some topics about magnetism from my electromagnetism course. This is part A. This presentation is part of a series of presentations with titles shown here, and they can all be downloaded from my website. The magnetism presentation deals with 27 topics, and in this part A we present topic 1 to 13. And we start with topic 1, the magnetic force on a current wire. Suppose we have a current here in a wire with total current is I and the cross section is S, and the cross section can be variable. The current density is defined as the IDS, the number of amperes per square meter. And the S is the cross section of a current element. Here, a volume element along the path carrying current. The length of this volume element is dl, and dl is scalar dl times et. When we consider one charge in the current in the wire, then the Lorentz force on that charge will be the factorial product of velocity and magnetic induction times the charge. And per unit of volume, you have to multiply this with the number of particles per cubic meter, n, and this means that the force per unit of volume is the current density J in part, and that is in amperes per square meter times B, and B is the magnetic induction. On the volume V, the force will be dF is J times B times dV, or you can also write that as dF is J factorial with B times ds dl for the dV. And since J can be written as J times the normal factor in the direction of the current, we end up with G times ds times Et times B times dl. This is for an arbitrary current, and we can simplify this to I, the current, total current, times dl times B. When we have a straight conductor in a homogeneous field, then this integration over dl will offer F, the force is the current times the length of the current wire times Et, that's the unit vector in the direction of the current, times the magnetic induction. And you can see that F, the force, is always pointing outwards the plane of drawing, perpendicular to Et and to B. Topic 2, the Hall effect. Suppose we have a block of material here, conductor, and suppose we have n charge carriers per cubic meter. There is a magnetic field and a current I. Due to the magnetic field, the charge carriers will be deviated using the right hand rule to the bottom of the block of material, and this means that there will be a build-up of an electrical field between Q and P. Here is Q and P. Q is positive and P will be negative. And in the stationary case, there will be enough electrical field to compensate for the magnetic force, and this means that Q times V times B for the magnetic force has to be equal to E Hall. So when we insert J is NQV is the current divided by AD, in which A is the width of the block and D is the height of the block, then we end up with E Hall is V times B velocity times magnetic induction, is given by the current over times B over the number of carriers per cubic meters times each charge times the cross section AD of the block. And this is called the Hall potential. Hall potential we have to multiply with D, and we end up with this expression for the Hall potential. So the field will build up until the Hall frequency, the electrical force will compensate the magnetic force, and then between Q and P there will be a potential difference that can be measured. So this is a prototype for a magnetometer. Now the magnetic field of a line current. We have BO and SAVAR. dB is mu naught times the current over 4 pi times ET factorial with ER. ET is in the direction of the current and ER is in the direction of point B, as you can see here, ER and ET, over R squared. And the question is, determine B in P. We have to do it with current line elements, and this means that the calculation of ET times ER factorial is E phi, the tangential unit vector, perpendicular to both of these vectors. And you can see that we only have a tangential component. And this means that dB can be written as mu naught E over 4 pi times sine theta over R squared. Now, suppose we maintain dz as the integration variable, then we end up with the expression 1 over the capital R squared plus z squared. Capital R is this distance and z is the varying distance. This is r little r squared, small r squared, and this is the sine of that angle theta. And when you integrate that, you end up with, you have to integrate that from minus infinity to plus infinity. What you also can do is use theta as a variable, then the distance small r squared, this distance to P, can be written as 1 over r squared and 1 over sine theta squared, as is seen here. And the sine theta from the formula, and this is dz. dz can be written in the form of r d theta over sine squared theta, because z is r over times tangent theta over time tangent theta, and dz is r divided by sine squared theta d theta. And when you integrate theta from 0 to pi, you end up with the result that the magnetic induction in B is tangential, is perpendicular to the current, and inversely is proportional to the current and inversely proportional to the distance. And you can see magnetic field of a circular circuit. Again, BO and SAVAR. The question is determine B and P, and we approach that with current line elements dl. dl is dl scalar times ET. For the calculation, ET times ER here is always 1, because they are perpendicular to each other. And since we have symmetry, there is only a y component. And that y component is given by the integral over the closed path, the closed circle, of mu naught I over 4 pi from BO and SAVAR times 1 over r squared times dl cosine alpha. And this is the cosine alpha is the cosine for the y component here. This is the total vector dB, here the y component. Here we have the expression for the r squared, that is 1 over a squared plus capital R squared, and capital R is the distance here, and a is the radius of the circle. A is the radius of the circle. 2πa is the integral over dl, the circumference, and a over the square root of a squared plus r squared is the cosine. And this means that the expression for point P is mu naught I over a squared divided by 2 times a squared plus r squared, and that is the small r squared to the power 1.5. Topic 5. Magnetic field of a circular solenoid. Here it is. Radius A, current I, length L, and the number of coils is N, or the number per meter is N. And the question is, determine B in point P. The approach is, a solenoid is in fact a set of circular circuits, and for each circuit we derived that BP is equal to mu naught times the current times the radius squared divided by 2 times a squared plus r squared to the power 1.5 times the tangential, the y component. We divide the whole circular solenoid in strips with width di, and it means that each strip carries a current di is n times dy times I. And when you insert that in the equation, we end up with mu naught times n times I times di, that is the current here, current element, times r squared, that's the distance, divided by 2 times the distance to the point P to the power 1.5. This is the distance r. This is the radius here, and we calculate the y here. And the y had to be integrated from 0 to L. And when you perform the integration, that's straightforward. The result for L goes to infinity will be B is mu naught n I times EI. So this is the number of coils per meter. This is the total current, and this is the constant mu naught. As you can see, the result is independent of the radius and the length of the solenoid. Now, magnetic forces between currents. Suppose we have two currents, straight lines, carrying currents I1 and I2, and the distance is R12. And the question is, determine the mutual force that current 1 exerts on current 2. The relations we have are relations for the magnetic field for current, in which E theta, that is the tangential vector, is equal to the factorial product of E along the current times ER, and ER is the vector to the point of interest. And dF is I dl times B, in which dl is the scalar dl times the unit vector along that force. Here we have the vectors. ET is the vector along the line, ER is the vector to the point of interest, and here we have the same. E theta 1 is the factorial product of ER1 and ET1 and ER1. Now, since E theta 1 is directed in this direction, we can calculate the magnetic induction that current 1 exerts on current 2, and that's given here with R12, E theta 1. And now we can calculate the force of 1 upon 2 is the integral over dl, the whole length, dl2, times E2 times ET2 times BL. That's the Lorentzian force on that current. And since B1 on 2 is directed in this way and ET2 is directed along the line, the force will be in this direction using the right hand rule. And you can see it here, ET2 times E theta 1, ET2 times E theta 1 factorial is minus ER1. And this means that F1 on 2 is a force in which the current wire 1 attracts current wire 2. When the two lengths are the same, then it means that F12 will be equal to minus F21. And you can see that as the currents have the same direction, the forces are attractive. When the currents are in opposite directions, the forces will be repulsive. An interesting point is why a wire is moved by a Lorentzian force, since inside the wire only the conduction electrons move, and only the conduction electrons are sensitive to the magnetic field. Well, how does a conductor look like? We have a fixed ion lattice and we have moving conduction electrons, as is shown here. What's happening now? Suppose we have a magnetic field perpendicular to the plane of drawing, as is seen here. An electron will feel a Lorentzian magnetic force in this direction. Because the velocity is in this direction, the B is in this direction, and the Lorentzian force is in this direction. This means that there will be a concentration of electrons at one side of the conductor. And this will cause that the lattice ions will feel a force Fe upwards. And this force is an electrical force. So the wire is moved not by a magnetic force but by an electrical force. And of course that electrical force is in the end originated by a magnetic force, but the force that the wire is causing to move is electrical. Now we go to the law of Ampere. Suppose we have a long, thin, straight wire with current I, then the question is calculate the circulation of the B field along circle L. Biot Savart is given, then the B is mu naught I over 2 pi r times the tangential unit vector. And when we perform that integration, we can perform E theta times dl, and that's just 2 pi r, the circumference. And this means that the path integral over the closed path of the scalar product of BDL is mu naught I, the Ampere's law. Here is Ampere's law again. The question is now determine the calculation of the B field along circuit C, and circuit C has an arbitrary shape. Let's take an element of circuit C. The element is dl here, and it spans an angle d theta. The radius, when you look at the radius here, r of the circle. Then we can write for the circulation as b times r d theta integrated over c is mu naught I over 2 pi r times 2 pi. And again we find the law of Ampere also for that arbitrary circuit. And this means that like we had in the Gauss case for charges, more currents through C will add up, currents outside C will not contribute, and the position of the current inside C is not important. The integral of BdL is always the same. We can use that in topic 9, the B field from a thick wire. And imagine a cylinder with a current I can be written as the current density integrated over the cross-section surface. And here we have the law of Ampere, and we can write it in the form of a path integral over a closed path, and then here as a current density integrated over the cross-section surface. And now we have two options for the current. First at the surface, or 2 in the volume, and suppose that when it is in the volume the current is homogeneously distributed along the cross-section. Now we use Ampere circuits. We can make a circuit inside or outside the cylinder. When the circuit is outside the cylinder, and that means that R is larger than the radius E, then this Gauss law is written here. We can integrate over 2πr, and this means that Br is mu naught I over 2πr, as we have seen before. But inside, first, in the first case, where the current is at the surface, Br will be 0, but in case 2, when it is distributed over the volume, then Br times 2πr is mu naught I over the amount of current that is passing through the small circular path, and this means that Br is linearly proportional to R here. We also can use Ampere's law in the magnetic induction of a solenoid. Suppose we have a solenoid with radius R and current I, length L, and the length is much larger than the radius, and the number of coils is n per meter. For the magnetic field, cylinder symmetry will be present, and this means that we will use cylinder components ER, E phi and Ez, the radial, the tangential component, and the component along the axis. Suppose we take a Gauss box inside the solenoid. This means that the total flux will be 0, and this also will mean that the flux from the top will be the flux in the bottom, and this means that the flux through the walls will be 0. And the consequence of this is that the R component of the magnetic induction, Br, as seen here, will be 0. Now we take another circuit. First, the circuit C in a circle outside the solenoid. This means that when there is when we perform Ampere's law, then you can see that B times phi is 2πr is 0 because no current is involved. There is no current going through that circle. And this means that B phi will be 0. Now we take circuit 2 and circuit 1. In circuit 2, BA and BB must be 0. And in circuit 1, when you perform that circuit integral here, then this part has a contribution. Bz times L is mu naught NIL. That's the current density here. That's the current that's breaking through that surface here. And the result is, inside we have mu naught n I times Ez, and outside we have B is 0. The consequence is that inside B is a constant field, independent on the position inside the solenoid. One remark: in this derivation here of circuit C, we have assumed that no current is breaking through that circle. Well, of course, there, when you have a lot of coils per meter, there will be one coil breaking through that circle. But the contribution of that field to the total field will be negligible. So normally this contribution is neglected. Topic 11. The symmetries for Ampere's law. Here is Ampere's law. The path integral over the closed path L is mu naught times the enclosed current, or in terms of the current density in amperes per square meter. We have already discussed this symmetry along a wire. Here is the symmetry with the solenoid, with a path crossing the wall of the solenoid. Here we have a solenoid with an infinite radius, a plane, and this is a toroid, and then the path integral will be taken along the core line. We take a plane layer L with current density J in amperes per meter height, current density J. Here we have the coordinates x, y and z, and the B field of that layer will be for circuit L. There is only contribution of this side and this side here. The B will be mu naught L JL, so BL will be given by plus or minus 1/2 mu naught J. And the direction is in the Z direction, along the path here. BL and BL here. Suppose we add an external field BE, with BE is BL, so that the total field behind the layer is 0. And this is to reflect the situation when you have a solenoid inside. This means that the Lorentz force on the green surface element, and the surface element here has a length dl and a height db, then the force element will be J times dB, is the current element, times dl is the length, dl, length, times B, 1/2 of mu naught J times Ez. And J factor times Ez, factorial product, here will be Ey along the y direction, and this is the expression for the force element. The df is in the y direction, because the J is in this direction and the B is in the Z direction. dBdl is a surface element, area element, and this means that the P is given by 1/2 over mu naught J squared, and that can be written as 1/2 over B external squared divided by mu naught. And you can see there is a magnetic pressure P moving to the right, and as an example, this situation is met when you have a long solenoid. Then the wall feels a pressure directed outward, and this means that the pressure will try to maximize the cross-section area. And there's also in a solenoid. The vector potential. Suppose we have a flow tube here with a current density J, and here we have a volume element dV prime. All points in the flow tube will be denoted by prime coordinates, and point P, where we would like to know the potential, the vector potential P, will be denoted by XYZ. And the question is determine the A, and the A is defined as in this relation here with B is the rotation of A. Please note that R is a function of 6 coordinates. The coordinates of the element and the coordinates of P. Now, from Biot and Savart, we have the expression for the magnetic induction caused by a volume element dV prime, and that can be written as in this form, in which ER over R squared is written in gradient form as minus nabla time of 1 over R. And when you switch the sequence of the components in the factorial multiplication with the J here, then we get rid of the minus sign. Now we use the chain rule. U dV is equal to d of uv minus v of du. This means that B can be written as mu naught over 4 pi times the volume integral, and now we have this part here, and that is the rotation of J over R minus the rotation of J over R dV prime. However, since the nabla operator in the gradient is a function of xyz, and the J is a function of x prime, y prime, z prime only, the rotation of J will be 0. And this means that the Bay field will be given by the rotation of J over R. Here it is. We can swap the integration and the differentiation, and we end up with this equation here. B is the rotation of this expression, and this expression is called the vector potential. The vector potential is the factorial integration of J over R integrated over the volume. This is the general equation, and this is the reduction of the general equation for a circuit.